Hello, my name is Tom Irvine, and I'm the instructor for this series of shock and vibration units. I again thank the NASA Engineering and Safety Center, NESC, and Dr. Kurs Larson for making this series of webinars possible. And today we're going to be discussing multi-degree of freedom system shock response spectrum. And previously, in our previous 27 units, we've covered a lot of concepts, a lot of basics, but today we're starting to get into the graduate school level of these webinars, and we will be getting into more equations. That's just something that we're going to need to do for these topics to make sense. So the SRS, it's inherently a single degree of freedom concept, but it is possible to extend it for the case of multi-degree of freedom systems. And there's two ways we can do this. One is that we can perform a modal transient analysis using a synthesized waveform. Now in the previous unit we learned how to synthesize a waveform to satisfy a shock response spectrum, and we could then take that acceleration time history and apply that as a base input to a spring mass model or within a finite element analysis. And the second way is a very fast technique. It's an approximation method that uses the participation factors and the normal modes or eigenvectors. And it's quick and it's pretty straightforward and simple, but it is an approximation method. So we've been discussing quite a bit single degree of freedom systems in the past 27 units. Well, today we get to graduate and we get to go on to the next level. And here we have a 2 degree of freedom system. So there are two masses, M1 and M2, and two springs, K1 and K2. And then we have the absolute displacement of each of the two masses and the absolute acceleration of the base. And this is only one of many different possible 2 degree of freedom systems, or more broadly, multi-degree of freedom systems. And you'll notice that there are no dashpots or damper elements in this diagram, and we could have put those in, but instead we're going to use an alternate approach, and we're going to apply damping as modal damping. And that will become more clear as we go further. So the next step is to draw up free body diagrams. So on the left we have mass 1, which is the bottom mass. Oh, by the way, let me go back and mention something. This particular diagram here is sometimes referred to as two-stage isolation. So imagine that we have a mass that we want to protect, and we could mount it via a spring or via even an isolator to, say, a ballast plate or base plate of some sort, and then that base plate itself is mounted via a spring or isolator. And this is a concept that is sometimes used to get increased isolation. But there are a few little caveats, and those will become apparent as we go on. One being that now instead of one structural mode, we will now have two structural modes to contend with. Okay, now back to the free body diagram. So here's mass 1, and this force pulling on it from the bottom is equal to the stiffness from spring 1. Then in parentheses we have the displacement of mass 1 minus the base displacement. Then this force pulling it from the top here is the second spring stiffness, K2. And then we have the absolute displacement of mass 2 minus the absolute displacement of mass 1. So we use Newton's laws to sum the forces, and that equals mass 1 times acceleration 1. And I'm going to skip over some of the intermediate steps, and really all of these equations I'm going to be showing to you are just sort of the highlights. And if you want the details, then you need to go to the papers, the reference papers that I have at my blog for this particular unit. So after going through a few steps and algebraic manipulations, we come up with this governing equation of motion for mass 1. So we have mass 1 times the acceleration of mass 1 plus, and then in parentheses we have the sum of the two spring stiffnesses times the displacement, absolute displacement of mass 1, minus stiffness 2 times the displacement of mass 2. And that is equal to the spring stiffness 1 times the base displacement. Now over on the right side we have mass 2, which it's the upper mass, and it has one force pulling on it, and that is spring stiffness 2 times the displacement of mass 2 minus the displacement of mass 1 in parentheses. And it's a little bit easier to do its equation of motion, so we sum the forces, and that equals mass 2 times the absolute acceleration of mass 2. And then that mass 2 times acceleration 2 plus the spring stiffness 2 times the displacement mass 2 minus stiffness 2 times displacement mass 1 is equal to 0. So those are the two equation of motions. And by the way, sometimes I'm going to refer to these as mass 1 and mass 2, but you could also think of this as being degree of freedom number 1 and degree of freedom number 2. And I'm going to kind of use those terms interchangeably, probably more than I should. And if we were in a finite element analysis, we might call this the mass at node 1 and this the mass at node 2, for example. And in a more complex problem, we could have up to 6 degrees of freedom per node for each of the two nodes. But for this case, we only have one translational degree of freedom in the same axis for both of the two masses. So the next step is to assemble those equations in matrix form. So we've got a couple of terms here. Here we have the mass matrix, and the mass matrix is symmetric, and it's in this case it's a diagonal matrix. So we have mass 1, mass 2 along the diagonal. The off-diagonal terms are both 0. Here we have a vector with the absolute accelerations of mass 1 and mass 2. Plus we have this stiffness matrix. Now it's also a symmetric matrix, and in this case though we have a coupling effect because this is a fully populated stiffness matrix. The terms on the off diagonal are non-zero, so we have a system coupled through its stiffness, and actually the coupling is really through spring 2. So if we go back to this diagram here, it's this spring 2 here that causes the coupling to occur. Okay, then we have our absolute displacement vector, x1, x2, and then on the right-hand side we have stiffness spring 1 times displacement, the base displacement. Now, in many cases when we're doing shock analysis, what we directly have is an accelerometer measurement characterizing the base input. So we do not directly know what our base displacement is in many cases. So to get this base displacement, we would have to take that acceleration and integrate it to velocity, and then integrate one more time to displacement. And that's doable, but it gets a little tricky, and the reason it gets tricky is because the initial velocity and the initial displacement are unknown, and we know from previous units if we take an acceleration time history and double integrate it, the displacement time history might have a ski slope effect. So it just gets a little tricky in that regards. What we would much rather do is transform this equation so that we could input the base acceleration rather than the base displacement. And that makes life a lot easier for us. So that's going to be our next step. Now, the system we're working with even though it's a 2 degree of freedom system, it is one step above our familiar single degree of freedom system. But this 2 degree of freedom system, it's really a very simple system. So we can go back to one of our favorite techniques, and that's looking at relative displacements and transforming this set of equations into a set of equations with respect to the relative displacement coordinates. Now I do want to mention here that if we had a complex system, maybe with up to 6 degrees of freedom per node, or for example we had a situation where there were multiple base inputs, then this technique would start to break down. But today it's going to work for us. Now when I say multiple inputs, imagine you're driving your car down the road and your front tires encounter a speed bump, while at the same time your back tires are encountering a pothole. So that would be a case of two different acceleration inputs into the same structural model, that if you were to make a structural model of your automobile. So for these more complicated systems and for multiple base inputs, we have to use another technique, and that's called the enforced acceleration method. And we're not going to cover it today, but we will cover it in an upcoming webinar. But anyway, so let's go and take a look at these relative displacements. Now, I could rearrange this, and I said, okay, the relative displacement 1 is going to be equal to the absolute acceleration 1 minus the base input. And then similarly for the relative displacement 2. But anyways, we go through and we take derivatives and do a bunch of substitutions and simplifications that I'm kind of skipping over, and we come up with this resulting equation of motion. Now our mass matrix and our stiffness matrix remain unchanged. They're the same as they always were. But now we have our relative accelerations, c1 double dot, c2 double dot, and we have our relative displacements, c1 and c2. And on the right hand side, this we're going to call this the forcing function eventually. We have minus m1 times y double dot, excuse me, that's the base acceleration. And then minus m2 times y double dot, that's also the base acceleration, y double dot being the same in each case. So, excuse me, I got to get a drink. So this is a better set of equations for us to solve, because we can directly put in our accelerometer data, y double dot. Or in the case if we have an SRS, we might synthesize an acceleration time history to satisfy that. And we can likewise apply that as y double dot. Now the next problem is these two equations, they're still coupled via the stiffness matrix. So we want to transform them into an uncoupled format. And I will say, however, there are ways to take this equation as is and to solve it using various types of, for example, the Newmark beta method. And you can read about that method in structural dynamic textbooks, and we're actually going to be referring to it later on. But the other way, which we're going to focus on, is decoupling this series of equations. And this will allow us to solve for Z1 and Z2, the relative displacements. Then we can also, from those solutions, we can calculate what the resulting accelerations are, C1 double dot and C2 double dot. And once we know the relative accelerations, we can go through the equivalent format of this with each term taken to the second derivative, and then we can back calculate what the absolute acceleration for degree of freedom 1 is, as well as the absolute acceleration for degree of freedom 2. So let's go through this uncoupling process. And just for simplicity, sometimes we'll take that equation and we'll take the mass matrix and just represent it by the uppercase M. And here I'm showing this relative acceleration in vector format. Plus we have our stiffness matrix here times our relative displacement vector, and that equals our forcing function. And even though this is base excitation with y double dots, for today we're going to call this the forcing vector, or force vector. That'll become more clear later on why we're doing that. So the way we're going to do our decoupling is we're going to use eigenvalues and eigenvectors. And our natural frequencies are going to be calculated from the eigenvalues. So I might get a little bit sloppy and just sort of use eigenvalues and natural frequencies interchangeably. And then our eigenvectors are the normal modes. These are orthogonal mode shapes. We'll be talking more about those. And the details for all of these derivations and transformations are given in the papers on my website, but we are going to go through some highlights here. So what we're going to do is we're going to take our homogeneous equation. So in other words, let's take this equation here, but we're going to set the right-hand side just equal to 0. That makes it homogeneous. And we're going to say that that relative displacement vector is equal to q bar here, which is going to be our modal coordinate vector, or eventually it's going to be the eigenvector, times the exponential here. Then in parentheses we have j. Well, that's just equal to the square root of -1, so that's our imaginary number. Omega is going to be the natural frequency in radians per second times t, which is time in seconds. So we're going to take this equation here and we're going to take some derivatives. So here's our assumed solution for a harmonic response. We take the derivative to go to relative velocity. So this j omega comes out from the argument and gets deposited here, kind of like a scale factor. Then going to relative acceleration, z double dot, j omega comes out again, and this term out front turns into minus omega squared. And then we have q, which is essentially the eigenvector, and times the exponential term. So we take these equations and we substitute them into our previous equation of motion. And I'm not going to be a college professor and go through all these terms by term. Really what I want you to do is, more than anything else, is just to get the overall big picture of this process. And you can go back and fill in the details later on at your leisure. So we can pull out this q bar exponential term with its argument. And in this term inside the curly brackets here, we have minus omega squared m plus k. And this, for our example, this mass matrix will be 2 by 2, as well as stiffness will be a 2 by 2 matrix. And it turns out we can solve this equation if we take the determinant of that term within the brackets. And that is called the generalized eigenvalue problem. Now when I say eigenvalues, they're actually going to be omega squared, where omega is the natural frequency in radians per second. And since for our example we have 2 degrees of freedom, we are going to have 2 eigenvalues and 2 natural frequencies, which means there are 2 eigenvalues that will solve this equation in terms of setting the determinant equal to 0. Now when you first took a linear algebra class back in your university days, you probably start off with the standard eigenvalue problem. And a standard eigenvalue problem would have the mass matrix set to the identity matrix. And in that case, identity matrix has 1s all along the diagonal, and all the off-diagonal terms are equal to 0. And that's the standardized eigenvalue problem. But we're solving the generalized eigenvalue problem, and our m could have various values along its diagonal. And when we get to more complex systems, n might even have off-diagonal terms that are non-zero. So this sets up our generalized eigenvalue problems. And again, k is the stiffness matrix, m is the mass matrix. So we solve that and get our eigenvalues and take the square root of the eigenvalues, and that gives us our natural frequencies in terms of radians per second, then divide by 2 pi to get our natural frequencies in hertz. Well, once we've done that, then we're going to go back and calculate the eigenvectors. So we have 2 eigenvalues. That means we're going to have 2 eigenvectors. So one at a time, we plug in the eigenvalues into this equation here, and then we solve for q. Now it turns out that for this q value, there are not going to be exact values. There's going to be an unknown scale factor involved in calculating these eigenvalues. Excuse me, these eigenvectors. Q is the eigenvectors. And with that, we can choose that scale factor to achieve a certain purpose, which will be shown to you here shortly. Okay, so I think what I'm trying to say is that there are two equations and there are two unknowns because there's two terms in the eigenvectors, but those two equations are not independent of one another, and that sets up the situation where we have an unknown scale factor. Now these eigenvectors describe the relative displacement of the degrees of freedom for each mode. And then the overall response for the case of free vibration, for the case of a homogeneous problem, the overall motion is a superposition of the individual modes. And also, even if it's just a forced response or base excitation response, those modes are going to figure into the response. So what we do is we take those eigenvectors and we arrange them in a column format. And I'm showing a hat here because we've normalized them. We've chosen that unknown scale factor a particular way to normalize these eigenvectors. And I'm going to explain that to you here shortly. But anyways, we have these four coefficients. So here we have Q1 and then 1 and then Q21. So this is going to be the first mode. So the second one here in each case is the mode number. Excuse me, the second subscript is the mode number. The first subscript refers to the degree of freedom. So we have mode 1, degree of freedom 1. Mode 2, degree of freedom 2. Then we have mode 2, degree of freedom 1. Mode 2, degree of freedom 2. And we're going to normalize these eigenvectors. Now there's a unique scale factor for each eigenvector. So we're going to take the transpose of this matrix Q, and then we're going to multiply it times the mass matrix, and we're going to multiply it by this eigenvector matrix, and that's going to come out to be the identity matrix if we've chosen our scale factors properly. And actually we can go ahead and run this calculation first, and we'll get whatever we get on the right hand side, and we force the right hand side to be the identity matrix by then going back and choosing the scale factor appropriately for each of the two vectors. Now once we've achieved this identity matrix via this relationship here, we can then take Q, this eigenvector matrix transposed, times the stiffness matrix times the eigenvector matrix, and that equals uppercase omega, which is a diagonal matrix of the eigenvalues. So in other words, those omega square terms. And the off-diagonal terms are equal to 0. So what we would call this matrix here then is we would call this the mass normalized eigenvector matrix. And that would be the formal title for that matrix. So the next thing we're going to do is we're going to define a modal displacement coordinate. And I'm embarrassed to say I've forgotten what that Greek letter is called, so I'm just going to refer to this as the modal coordinate. And we're going to say, okay, our physical relative displacements are equal to this mass normalized eigenvector matrix times the vector of our modal displacements. Now we're going to have two modal displacements since we have two modes. So right here, this is a 2 by 1 matrix, and Q is a 2 by 2 matrix. And then this would be, this modal coordinate here would be a 2 by 1 matrix. So we're going to take this and substitute to our previous equation of motion. So we have the mass here times the eigenvector matrix times the modal acceleration vector plus our stiffness times the eigenvector matrix times the modal displacement vector. And we're going to reintroduce our forcing function term here. Now we're going to pre-multiply through by the transpose of our eigenvector matrix, our mass normalized eigenvector matrix. So we have Q transpose mass, Q, and our modal accelerations, plus Q transpose, our stiffness matrix, our eigenvector matrix, then our modal displacement is equal to Q transpose times our forcing function. Now, here's where we can really take advantage of those previous orthogonality relationships, or our identities. because this term here out front of the modal acceleration is just equal to the identity matrix. Because for two reasons. One, we have a set of orthogonal or normal modes, and they have been scaled so that this term out in front of the modal acceleration is in fact the identity matrix. Then that gives us, for this matrix out in front of our modal displacement, this is a diagonal matrix with the eigenvalues, which are omega squared. Then we have our Q transpose times our forcing vector. So let's go and take a look at these in the full form here. So our two equations of motions that have been bundled into one matrix equation of motion. We have our identity matrix times our modal accelerations. Then we have our eigenvector matrix, or I should say matrix of eigenvalues. Yeah, let's call this, okay, I'm getting a little tongue-tied. This is the matrix of eigenvalues, which are the two natural frequencies squared. And here we have our modal displacement vector. Then this is equal to our eigenvector matrix. And here we have our base excitation functions. And since this is mass times acceleration in each case, we're just going to call this a force. Now, remember the damping. We want to add in damping. So we're going to do a little bit of hand waving here, but it actually turns out very well. And we're going to say that this system has viscous damping. Now, in terms of damping, I realize there can be viscous damping, there can be Coulomb damping, there can be other sorts of damping as well. But we're just going to stick with the simple viscous damping case. So we're going to introduce a diagonal damping matrix here, and we're going to introduce the modal velocity terms. So here we have 2, and this will be our modal damping ratio for mode 1 times our natural frequency for mode 1. And down here we have 2 times the modal damping for mode 2 times our natural frequency, our second natural frequency. And this is great because here we have a system of uncoupled equations. And these are easier to solve. So we're ready to go for a modal transient solution. Now, if y double dot here is just something simple like this, a sine wave or a cosine function, or even a half sine pulse, we could solve this in terms of Laplace transforms, and that would be a very good way to solve this because that would give us the exact answer. But what we're going to do instead, since y double dot could vary arbitrarily with time, so imagine y double dot is white noise or random vibration, or it could be an earthquake or a pyrotechnic shock, something that is just non-deterministic, I think is the word I'm looking for. So we're going to use a numerical method. Now we could use, there are other numerical methods we could use. There's a whole set of them. Probably the first numerical method you learned from solving differential equations was the Runge-Kutta method. And there are people who just, that's their bread and butter. But the problem is, for what we're doing, is that the Runge-Kutta method could become numerically unstable for so-called stiff systems. So if we're just doing low-frequency structural dynamics with very low natural frequencies, Runge-Kutta could be used, and in fact is widely used. Some of my colleagues use it for their low-frequency work. Then there's also the Newmark-Beta method, which the strength of the Newmark-Beta method is it can be used for a set of coupled equations. But of course it will also work for uncoupled equations. And the Newmark-Beta is probably the favorite method for structural dynamics textbooks. And if you look through those textbooks, you'll see there are other kind of cousin methods to the Newmark-Beta, like some Wilson method or Wilson pi or theta or something like that. But Newmark-Beta is probably the most prominent of that class of methods. And it's a pretty good method, but again, it's probably better suited to lower frequency analysis, like low frequency structural dynamics. And it will remain numerically stable if we use it on a pyroshock problem, but it starts to have some loss of accuracy once we get into high frequency modes and high frequency excitation. And the choice for this webinar unit and really more broadly is going to be another digital recursive filtering relationship. And you recall the Smallwood method, for example. And the digital recursive filtering relationship that we're actually going to be using in this unit is the same one from Unit 17. So I'm not going to show that equation again, but if you're interested, and in fact I encourage you to do this, is go back to Unit 17 and review the digital recursive filtering relationship for the case of an applied force. Now the Smallwood version was for the case of base excitation, and even though this is a base excitation case, we're transforming that base excitation into applied force. So we're going to use the filtering relationship that's similar to Smallwood's, but the coefficients are going to be different. And one of the drawbacks, though, about the digital recursive filtering relationship is it requires a constant time step. Whereas with Runge-Kutta and Newmark Beta, we can have a variable time step. And some of my structural dynamics colleagues that I sit next to, in fact, do have forcing functions or base excitations where they do have a variable time step. So that's what I like to use, for example, the Runge-Kutta method. Well, for choice number 3, what we're going to do, if we are given a time history that has a variable time step, we're going to interpolate it so it has a constant time step. So that's going to be our workaround. And accelerometer measurements almost always are going to have a constant time step anyways. Okay, so yeah, I talked about the first bullet already. Digital recursive filtering relationships are fast, they have good accuracy, they're stable, and we love to use them for modal transient analysis, at least I do. So once we've done our digital recursive filtering relationship to solve for the modal displacements, we can go back through this transformation via the mass normalized eigenvector matrix, and we can get our physical relative displacement. And once we get our physical relative displacement, we can also get our physical relative acceleration. Then we take our physical relative acceleration, add it to our base acceleration, and that gives us our absolute acceleration for each of the degrees of freedom, or you could also say for each of the two masses. Now we're going to talk a bit about participation factors and effective modal mass values. And I'm just going to give you an overview of these. These are calculated from the eigenvectors and the mass matrix. And they represent how excitable each mode is. And we might cover those in more detail in a future webinar, but for now, please go back and read this reference paper that I posted at my website. But anyways, the point is, if a structure has two modes, one of the modes is going to be more excitable than the other mode. In other words, one mode is easy to excite, and the other one is more difficult to excite. And that's typically true particularly for base excitation. Okay, so let's define this gamma here, and that's going to be the participation factor for modi. So for our 2 degree of freedom system, we're going to have 2 participation factors. And we're going to go ahead and substitute this for this, you could call it this coefficient for our y double dot base acceleration. And if we go back and work through previous equations to make all of this happen, we need to set these 2 gamma value here, these 2 mass participation factors equal to, okay, here we have our column format of our mass normalized eigenvectors, and then we have our 2 mass terms. So for our simple 2 degree of freedom system, calculating the participation factors is fairly straightforward. Obviously, for more complex systems where we have 6 degree of freedom per node and all that, the process can get a little more complicated. Okay, so let's talk about these approximation techniques for, and this is going to be for estimating the response of a multi-degree of freedom system for a shock response spectrum-based input. And there's probably a whole slew of methods, but here's probably the 3 leading ones. The first is called the absolute sum method, or sometimes we just say absum. It's the most conservative of the three, and it assumes that the peak response of each mode happens simultaneously. So that's a very conservative assumption. Then we have the middle method, the square root of the sum of the squares method, which is more just like kind of an RMS type of calculation. Then the third method is the Naval Research Laboratory method. And it turns out for a 2-degree of freedom system, the SRSS method and the NRL methods are the same method. So here's our absum method. Again, it's conservative because it assumes that all modal peaks occur simultaneously. So here we have our peak modal displacement for J would represent, J1 would represent the first mode, and then for our case, this uppercase N is equal to 2 because we have two modes. And then this I term here refers to the degree of freedom, or in our case, the mass number. So the relative displacement for mass I is less than or equal to this summation over two modes. And here we have the appropriate eigenvector coefficient, and times this, the maximum modal displacement for mode J. Well, the problem is we don't really know what these are unless we do a time domain calculation. And the idea, though, is we want to skip over that time domain calculation and just do something that's a little more direct. So what we're going to do is sort of a approximation of sorts, and we're going to say, okay, this modal displacement here, sub J, is going to be equal to gamma, so this is the participation factor. And over here we're going to have, in this case, there'll be the relative displacement value for mode J that's picked off directly from our relative displacement SRS curve. And it's picked off at the corresponding natural frequency for mode J. So the idea is that we take our SRS curve, we take our two natural frequencies for our case, and we find the two relative displacements from that curve, and then we just plug them in to this equation and take the summation, and this will give us a estimate for the upper limit of what our peak relative displacements will be for each of our 2 degrees of freedom. Now, I'm only showing these equations to you for relative displacement, but the same set of equations would apply for the case of our absolute acceleration. It's really the same pattern, so I'm just going to let you imagine that in your mind. And really it's pretty simple. Instead of having our relative displacement SRS value here, we would have our absolute acceleration SRS values here at the corresponding natural frequencies. And then this Z sub I would be x double dot sub I, meaning the absolute acceleration for each of the 2 degrees of freedom. And that's all the difference would be. So that's the absum method. Now here we have the square root of the sum of the squares method. And this is going to be approximately equal to the relative displacement at degree of freedom I is going to be approximately equal to this summation here. And we again have our eigen coefficient, or eigenvector coefficient. So for a degree of freedom I at mode J. And then we have our modal displacement, our peak modal displacement. And then we take that for each of the 2 modes and just do a square root of the sum of the squares method. Well, again, we don't want to have to go through and pick off what our maximum modal displacement is, because we'd have to go ahead and just do the modal transient analysis to get that, which defeats the purpose of doing this simplified estimation method. So instead, we're going to take this modal displacement here and represent it in terms of its participation factor, and also the relative displacement that we would pick off directly from the SRS curve. And then we take the square root of the sum of the squares, and that gives us our relative displacement for degree of freedom I, or in our case mass I. Now again, same pattern applies if we want to do this for absolute acceleration. So we would, for absolute acceleration, we would just pick off the absolute accelerations from our SRS curves. and do this calculation, and it would give us our x sub I double dot, the maximum acceleration at each of the 2 degrees of freedom. So that's just really kind of in a nutshell what it's all about. Okay, and the next part of this webinar unit, we're actually going to do an example, but I'm going to have that be part 2 in order to keep the time for each of these recordings under 1 hour. So please check back with us for part 2. So thank you for now, and see you soon.